I want to illustrate in a simple manner some possible approaches to quantum gravity, starting from the Einstein field equations that we can write, for example, in this form, g mu nu, which is the Einstein tensor, plus the cosmological constant, if you also want to consider this cosmological term, which is proportional to the metric tensor g mu nu, is equal to some constant that I will just call k, and then here we have the energy momentum tensor. Now this famous field equation describes the relationship between space-time geometry, the left-hand side, and matter energy content, which is the right-hand side, with the energy momentum tensor. Now starting from this equation here, this equation cannot be directly quantized in some conventional sense. And this can be explained in several ways. Let's start from the first point. The first important point is related to the nonlinearity of gravity. Nonlinearity. The Einstein equations are highly nonlinear differential equations, and this makes their analytical treatment challenging, especially when dealing with quantum superpositions and fluctuations. So in quantum mechanics and quantum field theory, we want to make use of the concept of superposition. But that's problematic, that's troublesome when we have this strong nonlinearity in the equations. And quantum field theory strongly relies on linear operators and perturbation theory, which are difficult concepts to tackle in such nonlinear systems. The second point that I want to address is the dynamics of space-time. Dynamics of space-time. In the Einstein equations, the geometry of space-time itself, which is the metric g mu nu, is dynamic. So it's also known as a background independent theory. I'm talking about general relativity. Relativity is a background independent theory, which means that this g mu nu here is dynamic. Unlike standard quantum field theory, where space and time are assumed to be fixed, and that's related to the concept of Minkowski space. So instead of g mu nu, in quantum field theory we have era mu nu, which is the Minkowski metric tensor. A third point that I want to address is the dimensionality and divergencies. Gravitational interactions are characterized by this constant here, which contains, so this constant is directly proportional to the gravitational constant, g, and this constant has a dimensionality which can be written as something of the order of 1 divided by the Planck mass, which I will write as mpl squared. So one can study the units of this constant, and it is proportional to 1 over this mass squared. And this means that gravity is non-renormalizable because gravitational constant has a dimension. This gravitational constant has a dimension. And one can show that this gives rise to lots of terms, and in particular infinite terms in the Einstein interaction when we consider larger and larger energies. And this contributes to the non-renormalizability of the theory due to the dimensionality of the gravitational constant. And this leads to severe divergences in quantum perturbative calculations. Infinities that can be cancelled only with an infinite number of parameters, but this of course is something that makes the theory non-renormalizable. Now, I want to address also a fourth point, which is the need for quantum geometry. Quantum geometry. The classical concept of spacetime described by the Einstein equations breaks down at the Planck scale, where quantum effects are shown to dominate. A proper theory of quantum gravity would quantize not only the metric but also the space-time itself. So, how can we approach quantization? This is a $1 billion question because it is something that physicists would like to do and are eager to do and have been eager to do for almost a century. While the Einstein equations cannot be directly quantized, several theoretical frameworks provide some approaches. So, one possible approach is the so-called perturbative quantization. So, here let me draw a straight line of separation between these points here, which are related to the difficulty in directly quantizing the Einstein field equations. And here I want to show you some approaches, I want to list some approaches related to how can we tackle quantization of general relativity. How can we actually do that? One point is related to perturbative quantization. Perturbative quantization. This method expands the metric tensor around a fixed background, which is usually the Minkowski space. So we have g mu nu equal to eta mu nu plus a perturbation that we can label as h mu nu. H mu nu represents small perturbations. This gives rise also to gravitational waves by working in this framework and thinking of h mu nu as something small. But this works indeed only at low energies. So for small perturbations, since divergences become larger and larger, stronger and stronger at higher energies, giving rise to an infinite amount of terms when we expand the Einstein invert action, and this is also related to point number 3 here. Now I want to address also another point, which is a semi-classical gravity. Semi-classical gravity. In this framework, in this approach, quantum states of matter fields influence spacetime with a classical metric. So we have the Einstein tensor, g mu nu, and let's assume that we don't have the term proportional to g mu nu, so we don't have lambda, which is the cosmological constant, plus g mu nu, but if you want, you can also generalize this. But this is something classical, and this is equated to the constant k, and then here we have an expectation of an operator, which is related to the operator of energy momentum tensor. So this is a quantum mechanical expectation value, and this is a semi-classical approach because we have quantized matter, but we have not quantized gravity. So this is still in its classical form. We don't have an operator on the left. We have an operator on the right, but we have taken an expectation value. So we can equate a number to a number. So this is a number because we are taking averages. It's not an operator. And when I say number, of course, I'm thinking of this as a number, but you also have to remember that this is a tensor. So for each mu and nu, you have different numbers. That's what I mean. So you have, if you want, a matrix of numbers. You can think of it that way. Whereas here you first have an operator and then you take an average and then you have a matrix of numbers. So that's the idea. Now, another possible approach is loop quantum gravity, which I will abbreviate with LQG. This approach directly quantizes the geometry. So instead of having a continuum, a space-time continuum, we have chunks of space. And I said space, not space-time, because loop quantum gravity, I mean, the first approach in loop quantum gravity is to quantize space and to treat time in a different manner, thinking of that just as a parameter which is not to be quantized. But I will not get into the details here. I will just mention some approaches. I have a course on loop quantum gravity if you're interested in more details regarding this topic. Then we also have, of course, the well-known string theory that I will abbreviate with just the initials S and T. String theory, in string theory, gravity is not described by directly quantizing the metric tensor g mu nu. Instead, the graviton is identified as one of the excited states of fundamental strings, with gravity emerging from the dynamics of strings. And this is something that completely overwhelms physics. It is something that completely changes the physical theories that we are used to more often than not. And some people like to argue that string theory might actually be an even larger framework than quantum gravity. It could contain actually all possible theories, not just the quantization of gravity, but other theories. And I will not get into this kind of topics. Of course, here this is just a list. Then let me also put another point here, point number 5, which is the path integral formalism. Path integral. So we might formally write down a partition function that is equal to a path integral. So we integrate over the metric, and this is the measure of the path integral, and then we have e, an exponential of I over h bar, the reduced Planck constant. Then we have an action that depends on g mu nu and possibly other fields as well, but this is a formal way of writing down a partition function which is used in quantum field theory. The problem is that it's very simple to write it formally, but it's much harder to do anything meaningful out of this because the integrals often fail to converge, making explicit calculations very challenging. Now, another possibility is formally that of canonical quantum gravity. Let me just mention it here as a sixth point, but actually this is also related to loop quantum gravities. It is connected to that, and in fact, in the course on loop quantum gravity, I also deal with a part of this problem because this is a very large, a very broad topic, that of canonical quantum gravity. And in particular, in this case, one can write down the so-called Wheeler-DeWitt equation, which is something related to the quantization of Einstein field equations, but actually it is a reformulation of the Einstein-Hilbert action. Actually, the Einstein-Hilbert action can be written in a different fashion, and this is quite technical, and I have provided details here. And there are other details in this course here, in the string theory course, and especially in loop quantum gravity though. But anyway, apart from that, we have a wave function psi, which depends on the metric, and then we have an Hamiltonian operator, which acts as a constraint operator on this function, and the result is zero. So this is some Schrödinger equation where we don't have the right hand side here. So for the Schrödinger equation, when the Hamiltonian acts on the wave function, this is proportional to the derivative of the wave function with respect to time. The problem is that in quantum gravity, actually in the theory of quantum gravity, this variable, this time variable, is meaningless. And the fact that the Hamiltonian acting on a wave function gives zero is some detail that I have provided here in this course. And the Wheeler-DeWitt equation that can be written in different ways, but explicitly we have to find a way to write the Hamiltonian, right? And I have provided a way to do that in the loop quantum gravity course, if you are interested. Anyway, this is very technical. It's quite difficult if you want to follow all these details. Of course, there is a plethora of articles that you can find online, that you can find in the physics literature. Anyway, to conclude this video, the Einstein field equations cannot be directly quantized in their classical form, but various quantum gravity approaches address how to capture the quantum nature of gravitational dynamics. And these are just some of them, not all of them.